So, building up to this discussion of geometric morphisms, I'm going to revisit this idea of how we can think of the functor category as exponential objects very, very briefly. Okay, so T times A is the product of category T and category A. If we have an arrow H comma F in that, then we can decompose it to H after identity A dash, after identity T comma F, or the other way around this square. Here, H is an arrow from T to T dash in category T, F is an arrow from A to A dash in category A. Now, if we think about doing this functor capital F, which is this functor from T times A, which is really the sort of origin of this information, if we do that on H comma F, then we can just imagine putting a capital F on everything in this diagram, and then the blue arrows will basically become we can think of them as components of a natural transformation from what the red arrows are. So basically the idea is a bit like this. If we have this kind of commuting diagram, if we do capital F on it, then we get this kind of situation as I've described with these equations. And then we can basically, if we define f of t underlined, we define that to be f after t exclamation mark a comma identity a. So basically this is just the functor which we have this object t of category t fixed, and then we get this functor from a to b, which is just like the way this functor f from t times a to b works, but with this t held fixed. Well, then basically we can think of f of h of identity a dash as the a dash component of this natural transformation, which we could call e to h, and we can think of e to h here as a sort of natural transformation from f of t comma blank to f of t dash comma blank, where h is an arrow from t to h dash. So the basic idea is that we can think that there's like, for every object of t, there's this functor f of t comma blank, which is essentially a functor from a to b, but the sort of copy of category A, which is in this product about this object, capital T. And then for every arrow of T, so for every arrow H, there's a sort of natural transformation E to H between the sort of corresponding functors, injecting, the T copy into B and the T dash copy into B. So I know I'm going through this too quickly. I urge you to have a look at the video on the exponential objects. But anyway, let me just actually tell you But yeah, anyway, the point of all this, the reason I'm saying all this is because basically the way that this arrow F bar works is it loads this information into the functor category b to the power of a. So F bar is going to send an object t of this category here to f t comma blank, which is defined like this. So this is going to be a functor from A to B. And also F bar, or F transpose if you like, is going to send an arrow of this category T, in other words, something like this kind of thing. It's going to send that to become this natural transformation e to h, which, as I've said, we can think of it as having an eighth component being capital F of h, comma identity A. And it's obviously a natural transformation from ft, comma blank to ft dash, comma blank. So we sort of get these functors and natural transformations from thinking about f, as I've described very fuzzily. And that's basically how f bar works, or f transpose. The other thing we need to describe is about how the evaluation arrow works. So how does the evaluation arrow work? Well, firstly, let me just say that b to the power of a is this category of objects as functors from a to b and arrows as natural transformations between such functors. And then I've already sort of described this, but let me just say it again. We have this functor f from t times a to b, and then the transpose of this is this functor from t to b to the power of a. It sends t to ft, comma blank. It sends this arrow h from t to t dash, this arrow to this natural transformation e to h I've already described. How does the evaluation arrow work? Well, the evaluation arrow is this arrow e from b to the power of a times a to b. It's going to send a functor g paired with an object capital A of category A to g of a. So it's just evaluating the functor on the object. Also, for a pair of arrows, so a natural transformation beta from g to h and a arrow f from a to a dash, it sends those to h of f after beta subscript a, which is like one way around this square. Or we could think of the results being this, they'll be the same. So, for example, if B was set and A is this this category of two parallel arrows, then we could think of the evaluation arrow as doing a sort of graph transformation and an action. Anyway, why do I say all this? Well, firstly, I want to talk about this geometric morphism and this one which comes up. Now, obviously, we now can understand about set to the power of c and set to the power of d as functor categories or exponential objects in the category of categories, as I've just been describing. But also, we can see where the kind of geometric morphisms come from a bit more clearly now, because we have this kind of arrow, f underlined, from D to C. And now, using the kind of theory that I described in my video on exponential objects, we can now consider this set to the power of f as this arrow that goes from set to the power of c to set to the power of d. And the way we set up such a thing in general is it's going to be the transpose of the evaluation arrow after the identity arrow set to the power of c times f underlined. So the thing is, though, we've just been talking about exponential objects and the different gadgetry associated with it, so we're in a position to be able to work out how these things work and basically see another way that the kind of precomposition geometric morphism thing that I've already been describing comes about. So we're interested in what's the form of this kind of arrow. So let's just have a look at it without the transpose for a start. So it's this, we're thinking about this composition of these blue arrows. So firstly, what's this? This is identity arrow of set to the power of c times f underlined, which we can write as identity arrow set to the power of c after p1, comma, f underlined p2. And then after that, we've got this evaluation arrow that we want to do. So let's just think, how does this composition of these blue arrows work on objects and arrows of this category at the top left here? So if we start with an object, capital X, comma D, so X is going to be a functor from C to set, and little d is going to be an object of category D. Well, if we do this first blue arrow on it, it leaves the X unchanged, and the D becomes f of D. And then if we do the evaluation arrow on this, we just get X of f of D. Now, that's what happens to objects. Now, what about arrows? Well, if we have an arrow of this thing at the top left, that's going to be a natural transformation phi from X to Y, paired with an arrow K from D to D dash. Now, applying this blue arrow, the phi remains unchanged, but this arrow K becomes f of K, an arrow from f of D to f of D dash. And then if we apply the evaluation arrow, this becomes y of f of K after phi of f of D. And let's call that composition K. So we could also write this as E after identity set to the power of C times F. But I mean, what we really want to do is work out the transpose of K. And we can do this now. We understand how transposes work. So we're going to be sending, K transpose is going to be sending X to K of X comma blank. Well, remember the way K worked. It sent X comma D to X of F of D. So it's clearly just going to send X to XF, which is what we expected. Now, also, how does this thing set to the power of F, how does it work on this natural transformation phi from X to Y? Well, if we recall, from here, we do the, we change the symbols appropriately. We get that it's going to change this to be this natural transformation eta of phi, which has its D component equal to K of phi of identity of D. So that would be y of f of identity of D after phi of f of D. But notice that all this stuff on the left here is just the identity with a load of functors applied. So it's just the identity, so we can ignore it. So the result comes out as phi of f of D, which is just what we've already seen. So the kind of conclusion to all this is that for this functor f from D to C, we have that this gives us this functor set to the power of f from set to the power of c to set to the power of d. And this really induces for us a geometric morphism. In fact, it's what's called an essential geometric morphism. So we've got a picture of this kind of thing happening in general. Well, I mean, here's a sort of nice picture. A bouquet, there's a functor from this category C here to set. So it'd be mapping this object here to a set of loops, this E' and this V' to a set of vertices, and S gets changed to become this kind of loop to vertex allocator. But then if we do this kind of functor after this functor F underlined, which goes from our kind of graph template, our sort of category of two parallel arrows, and what this is really doing is it is sending when we compose it with X, we're essentially making these kind of graphs where the source and target are the same and the same as the way the loops are allocated. And therefore, in sort of changing X to X after F, we're essentially changing the kind of functors which are describing these bouquets into these functors which are describing the same information, but in terms of graphs with self loops instead of the kind of bouquet loops. And the remarkable idea is that we can do this for any kind of, whenever we have like set to the power of C and set to the power of D, which we're interested in, and an arrow between C and D, we can do this kind of thing. But moreover, this resulting kind of functor is actually a geometric morphism. In fact, it's even stronger than that. So anyway, what is a geometric morphism? Well, this is the next thing I want to say. So a geometric morphism from a category E to a category E' consists of a pair of adjoint functors, F star being the left adjoint, so F upper star being the left adjoint to F lower star. So technically, it's these two functors, F upper star being the left adjoint to F lower star, where F upper star preserves all finite limits. So those two things together, where F lower star goes from E to E'. Well, those two things together constitute this kind of geometric morphism. Now, we usually call F lower star the direct image functor and F upper star the inverse image functor. And so basically it's this pair of adjoint functors where the one on the left preserves all finite limits. That's what we mean by geometric morphism. Now, an essential geometric morphism is the same kind of thing, but it also has the property that F star has a left adjoint. And this is the kind of scenario that we have with the kind of functor that I've just been describing. So I'm basically saying that I've got Yeah, so I'm basically saying that we can write this kind of thing as f underline star. And so it's going to have these adjoints, and it's going to be forming this kind of geometric morphism. So, like, to illustrate why this is such a cool idea, what I want to do is to just talk about some occurrences of this. I mean, if you remember the video on adjoint functors, towards the end of it, I was giving some kind of examples of the importance of adjoint functors, and I described some different kinds of ideas: free functors, co-free functors, discrete, co-discrete, connected component functors, different things which were all associated with different adjoint, with different adjunctions. And we saw that there's this very rich theory. Well, basically, you can get at all of that stuff just from thinking about a couple of kinds of these type of geometric morphisms, of which I've just been discussing in this video. But in fact, there are many more, like, other ones that you can get. So that same theory, and this theory I'm about to recap, can also be applied, for example, to this geometric morphism between bouquets and graphs that I've already discussed. So anyway, here's one example then. Suppose we have this category C, and we have this functor exclamation mark C, which goes from the category C to this category 1 here, which just has one object. Well then, if we apply the construction we've already discussed, we get this functor here that we could write as set to the power of exclamation mark C. This is going to be a functor from set to the power of 1, which is basically just set, to set to the power of C. And we could call this functor triangle. We could call it the discrete functor or the constant functor. How does it work? Well, it takes a functor S from 1 to set. We basically think of S as a set. It takes that to this functor S after exclamation mark C. And this is basically the functor which sends every object in the category C to this set S, and every arrow in the category C to the identity arrow of S. How does this triangle functor, this discrete functor, work on arrows? Well, it sends an arrow of set to the power of 1. In other words, it sends a function k from some set S to some set t. It sends that to eta to the power of k. And that's going to be a natural transformation between, well, it's going to go from one functor from C to set to another functor from C to set. And the way that this works is that for each little x in C, we have that the xth component of this natural transformation is just going to basically equal this function k, which is this function from S to t. So basically, yeah, we got a picture. So here's how our constant functor works. It sends these sets to these kind of objects of set to the power of c that have all of their components equal to that set, and then the function becomes this kind of natural transformation, but each of its components is just equal to the original function. So that's the basic idea. Let's see if we can be a bit more explicit about the real form of this. So the real way we can think of it, we can write the result as s after exclamation mark c. So this is just following the proper construction of set to the power of exclamation mark c using the previous results we have. So how we'd think of this s after exclamation mark c, well, it's going to be a functor from c to set. We could think of it as the result of doing this triangle functor on s. And so s after exclamation mark c sends an object e of c to s, and it sends an arrow of c to the identity arrow of s. To see this first bit, just think about what's s after exclamation mark c after e. So we can think of this, if we like, as the result of doing this functor s after exclamation mark c on an object e in category c. But we also see just from arrow composition that s after exclamation mark c after e is just going to be s. So yeah, this functor here, it's going to send an object e to this set s. So, like I say, this is our discrete functor. It's very interesting. Like, I advise you to compare with my video on adjunctions, my video on adjoint functors. If you look at that 2 hours and 50 minutes through, roughly, I talk about this very kind of interesting family of adjunctions which pop up in the study of these structured sets, and how for such a discrete functor, which is exactly this triangle functor I've just been talking about, which we could also now write as exclamation mark c upper star, well, we can call that the discrete functor or the constant functor, and I describe how it has a right adjoint, which is this points functor, and also it has this left adjoint, which is this connected components functor. So there's other really interesting things to do with this. In the way that these kind of adjoint functors work, particularly this connected components functor, and the fact that one can get these kind of things for these general kind of categories of sets to the power of c sheds a lot of light on, you know, how we can think of connectivity, and you can think of it in conjunction with ideas to do with sub-object classifiers and so on. Anyway, the other way around we can always go is, rather than thinking about this functor exclamation mark c, which sends everything into category c to the single object category, we can think the other way around. So suppose we have this category 1 here, which just is this category with one object, and then of course we have this functor e, which goes from that to the category c. So it's essentially picking an object for category c. Well, we can do the same kind of thing again. We can consider set to the power of e. That's going to be a functor from set to the power of c to set to the power of 1. It's the kind of thing we've already described. It's really the kind of it's really inducing this geometric morphism again, this essential geometric morphism. And so how does it work? Well, in this case, set to the power of c is going to send a functor x from c to set to this set x after e, which really is just the kind of functor x operating on e. And it's also this functor set to the power of e, it's going to send a natural transformation beta from functor x to functor y. It's going to send that to this function, which we could write as eta to the power of b. This is going to go from x of e to y of e. And it's basically just going to, well, it's really a function, so we can think of it as a natural transformation with a single component, that component being the eth component of beta. So it's really quite a simple kind of idea. So think about the case, again, in the category of bouquets, we have this natural transformation beta from this bouquet x to this bouquet y. And then if we do set to the power of e on it, we're just looking at the kind of what's going on in this situation when we're just looking at the eth components. So for an object e of category C, we have that set to the power of e sends a functor x to x of e. It's basically a set of e figures, and set to the power of e sends a natural transformation beta from x to y to its eth component beta subscript of e. And once again, if you have a look at 250 in the video on our joint functors, you see that we can really think of this set to the power of e, which we could also write as e star. We can think of that as this kind of forgetful functor, and it's going to have a left adjoint that's a free functor and a right adjoint that's a co-free functor. And these have, for example, very fascinating interpretations in the case where set to the power of c is the category of dynamical systems. So there's a lot more I could say about this stuff. These geometric morphisms are very fascinating. There's a lot more said about it in the book Generic Figures and Their Gluings. So I encourage you to check that out as well.